Hello friends, welcome to the lecture. In today's lecture we will discuss classical Fredholm theory for solving a Fredholm integral equation. So in the initial first thing is to discuss this kind of problem that if you remember we have solved this kind of problem. This is a Fredholm integral equation of second kind where the kernel kxt is given in terms of separable kernel. So kxt kernel is a separable kernel, and we have seen that the solution of equation number 1 is basically related to the solving of this kind of determinant, which we have obtained by putting the value kxt here in the equation and then separating in terms of aix and bit and keeping solving this we have already discussed. So from there we can get that the solution of this equation depend on the determinant of this kind d lambda, which is the determinant of the coefficient. Okay, so here this is the system y of x. By putting this and assuming your ci as a constant, then we can have this kind of system of equation. And when you solve this kind of equation where ci is your bit yt dt, so cit is given as integral bit yt dt, and aik is defined as bit akt dt, and fi is defined as bit ft dt. So if you look at, we need to find out only the coefficient ci, constant ci. If you can solve for ci, then we can write down our solution yt in terms of the ci. So here we know that the coefficient matrix is given in terms of d lambda, and here if d lambda is not equal to 0, then we can get solution like this. Let me write this again in an explanation. So here we have this y of x is equal to f of x plus, you can write it a to b k of x of t y of t dt. Then what we try to do here, we are just writing the expression for kst. So it is summation I equal to 1 to n. Let me write it what we have assumed here. Here I to n aix bit. So here we have aix and bit y of t dt. When you expand this, and you can write this as f of x summation I equal to 1 to n and a to b. Then this is with respect to t, so I can take out this aix out. So aix, then this is bit y of t dt. So by assuming this as ci, then I can write this as y of x is equal to f of x plus summation aix ci, I is equal to 1 to n. So it means that if you can find out the ci's, where ci is nothing but a to b bit yt dt. So it means that if you know the value ci here, then you can write down the solution yx here. So to find out this ci, we use the solution form and put it here, and then we can have a relation like this, ci as a to b bit. Now in place of yt I am writing this as ft plus summation. Now here you take k equal to 1 to n ak t ck, right, dt, and if you expand this, you will get ci equal to, and this is what k equal to 1 to n. I am writing this term out, bit akt. So here we can say that it is ck integral of a to b bit akt dt plus a to b bit f of t dt, right. So if you look at this equation number 3, it is basically the same thing. So here I am just writing here, by the way, here I forgot to mention this lambda, this one lambda here. So if you put lambda here, then we have a lambda here, lambda, and if we write it here, then this is a lambda here, and you can write it lambda here. Okay. So if you use the notation given here and as a equation number 4, I am using FIS BIT FT dt. So it means that if I use notation FI for this, and for this we are using AIK, then this is reduced to equation number 3. So this we can solve by a system of algebraic equation whose coefficient matrix is given as d lambda. This we have already discussed in case of in the lecture of separable kernel. So here the main thing is that how to find out these Ci. So here if you look at the d lambda here, so d lambda is basically what? So we can write this as d lambda, matrix of d lambda into C1 to say Cn equal to say F1 to say Fn, right? And then you can get your Ci as what? So how to get this Ci? So here your d lambda, let me write it. What is d lambda here? Here d lambda is given as, it is determined basically. So matrix will be given as this 1 minus lambda a11 minus lambda a12 and so on, minus lambda a1n, and here we have minus lambda an1 and so on, 1 minus lambda ann. So this is your matrix of d lambda. So I am just denoting this symbol as matrix of corresponding to d lambda, right? So here I can find out your Ck as what? So Ck I can get from dk upon d lambda. So dk lambda divided by d lambda by Cramer's rule. So what is this dk lambda? So dk lambda is nothing but you simply replace the kth column by your f1 to fn. So it means that dk lambda I am writing here as say 1 minus lambda a11, and at kth position I am writing f1 to say fn, and this is minus lambda an1, and here we have minus lambda an1n, and here we have minus lambda ann. So to find out this dk lambda we can get our Ck. Once we have Ck, we can put it in our equation this, and we can get our solution. Now I am saying that this process we have already discussed, but we are discussing it again in a different manner so that it will be generalized to find out a general theory for a general kernel. So here to find out this Ck, let me write it how to explain this. So here we say that your Ck can be written as, so here we can write it Ck as what? So Ck I am writing, we are expanding this determinant with respect to kth column. So when you expand it, it will be what? You simply write it f1, and then it is dk1, which I am writing it here. This we want to get that Cj I am writing in terms of f1 to fn with the help of cofactors here. So we want to write it Ck. So Ck will be what? You start with this f1 and then this, and this kth column is gone. Then what will happen here? f1, and we write it here minus lambda a21 minus lambda a2n. So what you will get? This is deleted and this is deleted. So what we have is this minus lambda a21. So kth column is simply gone, minus lambda a2n and so on. So this is determinant of this. So this is represented as the cofactor corresponding to position a k 1k. So this I can write it here as d of 1k. So here if you delete if you take this row out and this column out, whatever left we say that it is cofactor corresponding to the position 1k. So I am writing this as d1k. So I can say that ck is written as f1 d1k plus f2 d2k, right. So it means that when you consider f2 and then you remove this and this, then whatever left is the cofactor of corresponding to position 2k. So I am writing f2 d2k and so on. So this I can write it fn d of nk, right. And so ck is given as this divided by d lambda. So what we are doing here, we are just writing the expression of dk lambda in terms of cofactors corresponding to 1k, 2k and so on. So we can write ck as this. So once we have ck, we can obtain this ck, we can put it here and we can get our solution. So what we are trying to write here, so this is the expression cj given in terms of 5. So that in this way we can find out all the constant c1 to cn in this manner. So if you use this values of constants, we can put it back into a solution and we can write down the solution like this. So let me write it, our solution here. So here we are writing this solution as y of x is equal to f of x as it is plus summation lambda times summation I equal to 1 to n, and aix I am taking out, ci I am writing here. So this is your aix here, and ci I am writing here f1 d1i f2 d2i and so on fn d of ni, and divided by d of lambda here. So here, so solution can be written in terms of 6. Now if you further use the value of fi, what is fi here? Fi is given as a to b bit f of t dt. So if you use this notation, this we have already assumed that fi is this, then you can further simplify this and you can write this as f of x plus lambda times summation I equal to 1 to n, and I am taking d lambda out. So d lambda here, and this I can write it as ft, you can take it out. So it is a to b bi, I am writing f1. So bit, and this is d1i plus and so on. So f2 is what? So here it is b1. So f1 is b1t d1it d1i plus b2t d2i and so on, bn t dni, and this is with respect to dt, and whole it is aix, which we are representing it in next equation, that is here. So when we put the value of this fit, it can be written in this form, that summation j equal to 1 to n d1j b1t plus d2j b2t and so on. And if you write down in a simpler form, then this is nothing but summation I equal to 1 to n j equal to 1 to n dij bit ajx ft dt. Okay. So here I can write this as in a summation form. I can simplify this as, so here this I can write f of x plus lambda upon d lambda, and here summation you can take inside, no problem, a to b I equal to 1 to n. Now this summation I can write as summation say j equal to 1 to n, and this I can write it bj bjt dji, and this is so this is written like this, and you have aix, and this is over dt. So that is what is written as equation number 8. So I am writing equation number 8 as y of x equal to f of x plus lambda upon d lambda into this, which is integration a to b I equal to 1 to n, j equal to 1 to n, dij bit ajx ft dt, which I have written here. I think I forgot this ft here somewhere, ft. So what is ft here? I am putting this thing, so there should be ft here. So here we have ft. So we have ft here. Is that okay? And what is important here? Important here is that we can denote this whole thing as another variable which depend not only on x, so it will depend on x and t. So we are writing this as this thing. We can write this as equation number 8, and then we further want to simplify this. So to simplify this equation number 8, we consider another determinant of n plus 1th order, which is given in this particular format, which we denote as dxt lambda. So it is in first row we have aix, it is at 1 1 position it is 0, and the rest is a1 to an, and in the first column first position is 0, and we have b1 to bnt. Now by using this, if you expand this dxt lambda along your first row, then you will see that the term written in this summation, that summation I equal to 1 to n, summation j equal to 1 to n, dij bit ajx, this can be written as this single expression dxt lambda. So how we can look at, if you look at this aix, then it is what, let me if you expand this value, if you find out this value dxt lambda, then first thing is along 0, we are expanding along the first row. So if you first thing is 0 into this thing which is coming out to be 0, then we have a1x, and then this first, this is this column is gone, this row is gone, then what is left is your b1t, b2 to bnt, and this thing minus lambda a12, 1 minus lambda a22, and so on. And if you look at, it is nothing but this factor, this is nothing but you can write it a1 and this factor, right? So and we want to show that whatever be the expression given here is nothing but dxt lambda. So for that, let us write down dxt lambda. So I am just writing dxt lambda and try to show that whatever expression is written, this is nothing but dxt lambda. So this we want to show that this is your dxt lambda. So let us see how it is. So we are defining dxt lambda is 0, a1 x, a2 x, and up to anx, and here we have b1t, b2t, and so on. Here it is bnt, and then we have expression for 1 minus lambda a11 minus lambda a12, and so on, minus lambda a1n, and here we have minus lambda a21, and so on. So last one is minus lambda an1, and here we have 1 minus lambda ann. Right, now we try to expand this dxt lambda and try to show that we are getting this. So we are expanding this dxt lambda along the row. So if you expand this along the row, this will not contribute anything, and then we look at this a1. So here when you write this as, then we have a1, and then what is left here, then here we have this row out and this row out. What we sorry, this is gone, this is gone. So we have determinant of this b1 t and up to bnt, and here we have one say minus lambda a12 minus lambda a1n, and here we have what is this, this is gone. So here we have minus lambda an2. So here we have minus lambda an2 and 1 minus lambda ann. Now plus a minus a2. So here we have a2, and and so on, right. Now we try to identify what it is written here. Now if you look at, if you want to find out the determinant of this, then it will be what? It will be, now this time when we expand this determinant, we expand along the row, along the column, first column, that is b1t to bnt. Here we do it along the again the first column. Okay, let us see what is a2 here. So here when you take this a2, then we have b1 to say bn here, and then we have what? We have this 1 minus lambda a11 and so on. We'll write it. Now if you look at this, what is this? So here expanding this, we will have what? We will have, I'm just expanding this. So here we have b1, and then whatever is left is nothing but your what? It is nothing but d11, right? So that is this expression, and similarly you can write. So here we have, so here we can get the coefficient of a1 is what? A1 is b1 d11, and when you, and then you have b2, and then this row and this row is gone, this row and this column is gone, and then you write it, then it is d12 and so on, right. And similarly when you do it for a2, then you will get the similar expression. So this is a little bit calculative, so you try to expand it. So what we are trying to do it, we are trying to expand this along the first row, and then we have this, and then we find out the determinant of this along the first columns, and when you do this, you will get that a1 and whatever we have is b1 d11, b2 d12 and so on. Similarly you can find out the coefficient of a2 and a3 and so on, and when you simplify this, it is nothing but this summation I equal to 1 to n, j equal to 1 to n, bjt dji aix, this you will get. So it means that this expression, this you are getting as the determinant of dxt lambda. So when we do this, then this expression y of x can be written as f of x plus lambda a to b. We are writing this as dxt lambda divided by d lambda f of t dt, right. So this we are summarizing in this matrix. So here this dxt lambda is defined in equation number 9, and we are solving this by developing it by the elements of the first row and the corresponding minus by the elements of the first column. We find that expression in this bracket, this bracket is nothing but the dxt lambda. So it means that our solution can be written as this: yx equal to fx plus lambda a to b dxt lambda upon d lambda ft dt. Now here if we denote this as say gamma xt lambda, then we can write our solution in terms of equation number 11. So here I am assuming, here we are just denoting dxt lambda divided by d lambda as gamma xt lambda, known as a resolvent kernel, and we can write as our solution yx as f of x plus lambda a to b gamma xt lambda ft dt. So here if you remember, we are dividing this expression dxt lambda by d lambda. So here I am assuming that lambda is such that we do not have say 0, d lambda is equal to 0. So here I am just assuming that lambda is such that d lambda is not equal to 0. In that case, our solution is given in terms of y of x equal to f of x plus lambda a to b gamma xt lambda ft dt, where gamma xt lambda is defined like this. So if you know d lambda, if you know dxt lambda, which is defined like this, then you can find out our solution yx in this particular format, right. Now with the help of this, we try to find out say solution, and here we are saying that if d lambda is non-zero, then we have a unique solution here, but if d lambda is 0, means we have a lambda which is the 0 of d lambda, or in some sense we can say that lambda is the eigen value of the coefficient matrix d lambda. Then we have in that particular case we may have solution or we may not have any solution. So this we have already discussed, but again I am repeating it. In this case we may have zero solution or we may have infinite many solution. So this we can write it here like this. So either this integral equation yx equal to fx plus lambda a to b kxt yt dt with fixed lambda possess one and only one solution, that is corresponding to d lambda not equal to 0, and that is similar to say that when f is 0 then y is 0. So it means that when d lambda is non-zero, then you can simply say that f is 0, it means that your ci's are all 0 and you can write down your solution as y equal to 0. So here I can say that if d lambda is non-zero and you do not have ft here, then all this part is 0 and we can have y as 0 solution. So we can say that either this will have a unique solution, one and only one solution, or the homogeneous part will have trivial solution. But if d lambda is equal to 0, then we have to simplify and we can say that we have to do further analysis, and we can say that we have homogeneous equation. This may possess a finite number n of linearly independent solution. What is this y naught j from 1 to n? This is the nothing but the eigen function corresponding to this homogeneous part. So this we can always discuss. Now please remember here I am dividing by d of lambda, so it means that I am assuming that d lambda is never 0. So it means that this expression 11 is true for all those lambda for which d lambda is non-zero. Now what happen when d lambda is 0? So it means that it may happen that lambda is the root of d lambda, or you can say that lambda is an eigenvalue corresponding to d lambda. In that case what should be the condition on your f, or what should be the condition? So that we will discuss in next lecture. So here we will conclude that if d lambda is non-zero, then solution is given in this, and this is kind of a unique solution, and we try to find out when d lambda is 0 then what will happen. Okay, so thanks for listening us, I will meet in next lecture. Thank you.